The blocks world is a popular application area for illustrating ideas in the field of artificial intelligence. Typical blocks world scene is shown here. Now, most people looking at this figure interpret it as a configuration of 5 toy blocks. Some people conceptualize the table on which the blocks are resting as an object as well, but for simplicity, we're going to ignore it. In order to describe this scene, we adopt a signature with 5 object constants, A, B, C, D, and E, with 1 object constant for each of the 5 blocks in the scene. The intent here is for each of these object constants to represent the block marked with the corresponding capital letter in the scene. In a spatial conceptualization of the blocks world, there are numerous meaningful relations. For example, it makes sense to talk about the relationship that holds between 2 blocks if and only if one is resting on the other. In what follows, we're going to use the relation constant on to refer to this relation. We might also think about the relation that holds between 2 blocks if and only if one is anywhere above the other. In other words, the first is resting on the second, or is resting on a block that is resting on the second, and so forth. And what follows, we'll use the relation constant above to talk about this relation. Then there's a relation that holds of 3 blocks that are stacked one on top of the other. We use the relation constant stack as a name for this relation. And we use the relation constant clear to note the relation that holds of a block if and only if there is no block on top of it. And we use the relation constant table to denote the relation holds of a block if and only if that block is resting directly on the table. All right, now given this signature, we can describe our blocks world configuration by writing ground literals that state which relations hold of which objects or groups of objects. Let's start with on. The sentences here tell us directly for each ground relational sentence involving the on relation whether it is true or false. So in this case, A is on B, B is on C, D is on E, and the rest are all false. We can do the same for the other relations. However, there's an easier way. Each of the remaining relations can be defined in terms of on. These definitions, together with our facts about the on relation, then logically entail every other ground relational sentence, or its negation. And hence, given these definitions, we do not need to write out all of these additional ground relational sentences. So, for example, we can define the concept of clear as shown here. A block satisfies the clear relation if and only if there is nothing on it. For all y, clear of y is true if and only if there does not exist an x, such that on xy. And a block satisfies the table relation if and only if it is not on some other block. For all x, x of table of x if and only if there does not exist a y, such that on xy. 3 blocks satisfy the stack relation if and only if the first is on the second and the second is on the third. The above relation is a bit tricky to define correctly. One block's above another block if and only if the first is on the second, or it is on another block and that block is above the second. Also, no block can be above itself. Given a complete definition for the on relation, these 2 sentences determine a unique above relation. The main lesson to be taken from this example is the way that logical sentences can be used to define new relations in terms of existing relations, and thereby save us the effort of writing out all the ground atomic sentences that we would have to write out otherwise. This exercise tests your understanding of these concepts by asking you to say what happens when we drop the second sentence in the definition of above.